Great. So hi, everyone. I'm Valerie Hayot-Sasson, and joining the bandwagon of people confused with their affiliations. So I am soon to be an assistant professor at École de Technologie Supérieure, but previously was a postdoc at Globus Labs at the University of Chicago. And I'm presenting work that is was part of my postdoc, which was on facilitating reproducibility for HPC specifically. So first, we know that reproducibility is very important, and a very important principle for the scientific method. It helps us make sure that results that we obtain are not outliers or due to errors. However, that doesn't stop many research results from not being reproducible. And the reason, or some of the reasons why they might not be reproducible can be due to the fact that methods and code have not been shared, or also the input data that was used to generate the research output was not available. And another one could be that not enough repetitions were performed to generate the output. And so the lack of reproducible research has resulted in the emergence of many tools and initiatives to facilitate and promote reproducibility. They help researchers basically share their code and research data and provide ways for other researchers to search upon that metadata. Sorry. Okay, so before we continue, a bit of terminology. I'm sure everyone here is familiar with it. Sorry. So the first one, we're sticking with the terminology that was defined, or not defined, but is used by the ACM, as this is specifically for computing. So the first one is repeatability, which is the same team. So let's say I create research software and I want to make sure that my results are repeatable. I will use the same methodology, so same system, rerun my experiments, and hopefully obtain the same results. The following one is reproducibility, and with reproducibility, it would be an independent researcher that wants to follow my methodology and hopes to obtain the same results. So if it's reproducible, they will obtain the same results. And finally, there's replicability, which is an independent researcher or independent research team. They use a different experimental setup, and this could be, using a different operating system, using a different GPU, and seeing if they obtain the same results. For today, we're mostly focused on reproducibility, but touch a little bit on replicability as well. So HPC results can be particularly challenging to reproduce, and the reasons for this. So one of them is that some of the experiments require large amounts of resources. So if I'm trying to reproduce an experiment that uses 1,000 nodes and I don't necessarily have access to it, then I wouldn't be able to reproduce that experiments. There's also the need for specialized hardware. So access to, say, an Intel GPU might not be easy to come by. And in which case, if the result depends on access to that infrastructure, I did not have that infrastructure, then I would not be able to reproduce the results. A lot of the methods for reproducing scientific research results are based on the cloud, or they use the cloud. But because 1,000 nodes could be very expensive to execute on the cloud, and also getting specialized hardware is not necessarily easy to come by on cloud solutions, using the cloud is not necessarily a viable solution for HPC results. And as well, so the last thing is okay, so if we need a specific infrastructure and a specific subset amount of resources, we can try to access the same resource. However, access to these sites are often restricted, which means that security restrictions kind of prevent other independent researchers from reproducing results. And now, reproducibility evaluations take significant time and effort for both authors and reviewers. Authors have to write all this documentation to make sure that the results are reproducible, and reviewers have to try to get access to the infrastructure set up the code and make sure that it produces the same results, which can take a significant amount of time. And the final output may be that it's just not reproducible because access to the required infrastructure is just simply not available. So looking into what is currently done in high performance computing, we have the reproducibility badges that are there to incentivize reproducible practices or reproducible research in HPC. And they have been introduced in many conferences. Most of the definitions that I'm following or going off by are those SC. I'm just naming 3 of the badges defined by the ACM, but I believe there's something around 5 or 6. The first is artifacts available, which means that all the artifacts are publicly available and have a DOI attached to it. Then there's artifacts evaluated functional, which means that independent reviewers were able to, or there was sufficient documentation, one, and independent reviewers were able to install the software and execute it. And finally, there's results reproduced, which means that the main findings of the paper were reproducible. We also contacted the SC reproducibility chairs of the previous years to try to get an idea of how many papers get which badges. So if you get reproducible, technically you get functional and available as well. Functional, you'll just get available, and available is just available. So what we can deduce from this figure is that many papers are considered fully reproducible. That means they got all the badges, but there still remains a majority of papers that are difficult to fully reproduce or just not reproducible at all. And this could be the authors didn't even try to get any of the reproducibility badges. And so thinking about this, we were wondering, well, do we need an independent reviewer to ensure that the results are reproducible? And can we just make it all automated instead and just say, well, if a machine can basically reproducible results, then we can conclude that the results are reproducible. So we thought about using continuous integration, which is a software engineering practice to regularly test code to make sure that changes don't introduce new bugs. This would be used for automation. As well, using CI for reproducibility has actually previously been explored for specific use cases. So one example was it was employed in neuroimaging, and another one was in signal processing. But this hasn't been expanded on much since. And so how can CI be used to tackle reproducibility challenges in HPC? Well, first of all, it ensures that all the instructions, data, code, metadata is all machine and human readable. It will document the execution runs. So, I mean, if you're using a public CI, then other researchers or people can view the reproducibility runs and potentially access the logs if they are made available. Finally, it will also repeat experiments periodically. So if there are software updates on an HPC system, let's say, and it renders the results irreproducible, we can also capture that. And so what we did was we built this GitHub action called correct that is able to execute on any computing resources using Globus compute. So as a GitHub action, making it a GitHub action enabled us to use this notion of GitHub environment secrets, which you can force review on use of on like execution of the workflow, which meant that people who had access to the HPC sites could review the code that would be executed at that site before that code was executed on the site. And yes, so we can automate these reproducibility evaluations on various infrastructure and then receive the results and see the reproducibility runs being executed publicly. So how does correct simplify reproducibility for HPC? Well, the instructions for running are all publicly available. So you have the workflow that was used to reproduce the execution, all available on GitHub. We have the logs that can be persisted of the execution, so you can see exactly what was ran, what result was obtained, and it's for a period of up to 3 months with GitHub. But looking into other ways to persist this for longer. We have simplified replication. So that means that if you want to execute the same workflow on a different infrastructure, you can fork the repository and just simply modify the workflow with your Globus endpoint UUID and reproduce it on your endpoint. Finally, with the use of GitHub environment secrets, we were able to ensure secure execution. So automated workflows would only execute after code was reviewed and approved by the person with access to the computing sites. How do you use it? Well, first you would configure and start your Globus endpoints on the machine which you would like to reproduce the run on. Finally, you would store the Globus secrets as environment secrets on GitHub within the desired repository. And here you see I've listed myself as a required reviewer. That means that any PR or any commit would have to be reviewed by me before the run would, or the workflow would run on my computing resource. Then you would create a GitHub action workflow that specifies which environment to use and defines the command that you would like to run or your reproducibility run on the remote resource. We accept registered functions and shell commands for this. So here you can see that it was written out, the pip install and the execution of PyTest. And finally, if you can add another action to it, which persists the execution outputs onto GitHub for that period of 3 months, that would allow other users to pull these logs and see and get a view of the reproducibility run. And just a view, like looking at how it's executed across sites. So you define your resources. It's just Globus endpoint UUID, the cache, the clone endpoint, or the endpoint config and the cache. You wait for it to execute at the various sites. So here we have 3 sites. You can download the execution logs once the run concludes, and then you can create your figures with those results. So here we just ran PyTest on a protein docking code and just got the execution time of each PyTest call and then compared them between the 3 sites. So right now we have correct that facilitates reproducibility on HPC systems by relying on recipes to automate the execution and provide real-time logging and temporary storage of the outputs. There are still a few things that we would like to look at. So we want to explore alternative methodologies for authentication. Basically, right now, a reviewer needs to, every time a commit is performed, a reviewer or the person with access to the site would need to review the code that is going to be executed and approve it. So this is not exactly automated. So we want to see if there's a way that we can keep the security aspect without having to have a reviewer approve the code each time. And investigate the necessity and applicability of continuous reproduction for large-scale runs. So if you have 1,000 nodes, maybe you don't want that running every week. Is there a way that we can ensure that it's reproducible, or like reduce the frequency and still ensure that it's reproducible? So exploring how often we need to run these large-scale runs, and can we do something smaller perhaps? And finally, investigate solutions to persist all outputs and not just the standard out and standard error. So now at this moment, what we get from Globus Compute is just a standard output and standard error back. But sometimes when you execute code, it generates files that we would also like to capture and maybe persist that in some public location. So that is something that remains to be investigated. All right. Thank you. So yes, I would love to hear about people using correct or leaving me feedback. So please do not hesitate to create issues or PRs or email me with feedback. Thank you.